friends, welcome back. After the whopping 40 views I got on my last video, I thought why not keep the momentum going and put another video out this week. Today we're gonna be learning about databases, but before I get into that, if you're new to this channel, hi, my name is Gigi. I'm a senior software engineer. The whole idea of this series is to deep dive into different topics to become a better engineer, and this will also help us prepare for interviews. All right, so enough with the yapping. If you like this video, like and subscribe for more, and let's get into the lesson. All right, so today's lesson is going to be all about databases. We know what a database is. We know it's supposed to store data. When we give it something to store, it's supposed to just give us that data back. But how does the database actually query that data on disk? How does it store it efficiently? How can we access it efficiently? And how can we make sure that if anything happens and the database crashes, that our data is safe? So to answer those questions, let's just start with the request flow. So when the database first receives a request, it writes to something called a transaction log. So here's an example of what a transaction log might actually look like. Now, depending on the type of database you use, this can be called a commit log or a transaction log, but it's all pretty much the same concept. And this transaction log is special for two reasons. One, it's durable because it's written to disk. So this means that if any crashes occur from the time that the database first receives the request to the time that it actually writes the data to a table on disk, we are able to replay those transactions and recreate the correct state of the data. Secondly, writing to this transaction log is actually really quick. And the reason it's quick is because it's append only. Multiple writers can write to this log concurrently, and they don't need any complex locking mechanisms because you're always writing to the end of the log. All right, so after we write the data to a transaction log, this data goes to what's called an in-memory buffer. And you can think of an in-memory buffer as a holding spot before we actually write the data to the correct spot on disk. So there's a few reasons why we want to hold this memory in this buffer before we write it to disk. One is because writing to disk is relatively expensive. So we use these buffers as temporary storage so that we can batch these writes and reduce the amount of I/O operation. This will help us improve performance. Now, the second reason why we like these buffers is because reading and writing to memory is fast. So if a request comes in, we can first check this in-memory buffer to see if it has the key. If not, then we can do a disk access. So now we only have a certain amount of RAM, so we don't want to make this buffer too big. So we periodically flush it to disk, and that's going to be the next step. So finally, as I said, after the data is written to this buffer, it's periodically flushed to disk. And this data is flushed in units of storage called pages. So a page is a unit of storage between 4 kilobytes and 16 kilobytes, depending on the database. And this is how the database organizes the rows and columns. So when you make a query to the database, what it does is finds the page that the data is located on, loads it into memory, and then finds the offset which the row is located. Now, as you can imagine, if we have a lot of data in the database, there's probably going to be many different pages. And sequentially searching through all these pages probably takes a lot of time. I'm sure the first thought in your head is, why not use a hash table to store a key to the place it's located on disk? And actually, databases do that. And this is what's called a hash index. So an index is an additional structure the database stores in order to optimize reads. So before the database writes this data on disk, it updates the structure so that when we retrieve that data from disk, it's a lot faster. So as you can imagine, this does slow down writes because we had to update two structures, but it does speed up reads. So let's get back into the hash index. So as I said, a hash index is an in-memory data structure, and it's basically a hash map which stores the key to the place where it's located on disk. So the page and the offset. Now, this hash index is great for a few reasons. One, obviously, it's constant time lookup. It's an easy structure to maintain because it's just a hash table. It's in memory, so it's quick. And there's not much overhead because there's no sorted order to maintain. So the problem is, what if we have a really large key set? Now, this hash table is going to take up a lot of memory. Also, there's no way we can do range searches on this hash index because the keys are not in a sorted order. Finally, say we have a lot of updates to different keys. This is kind of inefficient because we need to update the size of the hash table in memory. So that leads us to the next type of index, which does a few things better. So this leads us to the next type of index, which is called an SS table. This is also referred to as LSM trees. So a sorted string table is an immutable data structure that we use to organize the data in a sorted way on disk. So the request flow pretty much works the same way as I said before. First, we write to the commit log, then we write to an in-memory data structure, and then we write to disk. The only difference is that this in-memory data structure is actually going to have the sorted data. So we use a tree structure. I'm sure you remember from computer science classes, we had those red-black trees, we had those ABL trees that are able to maintain keys in a sorted order. That's exactly what we use to store the data in memory before writing to disk. So one special thing to remember about SS tables is that they are immutable. This allows our writes to the database to be very quick because the database is doing sequential writes. If you remember, I mentioned the benefits of sequential writes when I talked about the transaction log earlier. Okay, so say we have an SS table and I already made an update to my username. So let's say I set my username to Gigi. Now, later on, I want to update that username. Now, because SS tables are immutable, a new SS table will be created. So now you must be wondering, how do we maintain consistency? Because now the database has 2 copies of what my username is. Well, SS tables do something called compaction. And this is where we combine these SS tables into a single SS table with deduplicated keys. Now, when querying these SS tables, it is more efficient because the keys are in sorted order on the page, but we also need to maintain some index because we do need to know what the root of these SS tables are, so we can quickly know which SS tables we need to query. So the database does maintain a sparse index, and this just contains a few keys and their location, so that when you're performing a lookup for a certain key, you know which SS tables to check. So when a request comes in, we first check the in-memory data structure to see if the key is located there. If not, we query the SS tables that we find using that sparse index. And we can do kind of like a binary search because the keys are sorted. Now, along with the sparse index, we also can use Bloom filters to check for the existence of a key within an SS table, and this also speeds up our read queries. So an SS table does have a lot of pros, right? We see that the keys are sorted so we can do our range queries. Writes are fast because it's sequential writes to disk, so we don't need to do too many disk seeks. And because the data is sorted, our lookups are going to be O log n, which still beats not having an index at all. Now, there are still a few cons to SS tables. As the number of SS tables grow, the frequency of compaction needs to be tuned. So if you don't have the right tuning on your compaction rate, database has to query more SS tables. Now, we do have the Bloom filters and the indexes to make this more efficient, but it's still going to take some time. Also, compaction is expensive, so the read throughput and write throughput might slow down during this time. So SS tables are used in databases which require high write throughput. So think NoSQL databases and key value stores. So when you're doing your system design interview, remember that if you require high write throughput, databases with this type of index might be your best choice. Okay, so what if we have an application that does a lot of reads? This leads us to our last type of index, which is called a B tree. And this is actually the most commonly used database index found in relational databases. B trees are similar to SS tables in the sense that they store the data in sorted tree form, but B trees are actually mutable and they're stored in concepts of pages instead of SS table segments. So an SS table segment can actually span multiple database pages, but B trees correspond to database pages. So one B tree can be either 4 kilobytes, 8 kilobytes, or 16 kilobytes. So because B trees correspond to database pages, you can think of the pages of a database as nodes of a tree. So let's say we have a root node where there's a single database page, and this root node can contain multiple different keys. And each key on this page contains values which can be pointers or references to other database pages. So to update a key, you start from the root node and you do a traversal to different pages in order to find the leaf node, which is the actual value you want to update. So now you're probably wondering, what if I want to insert a key, but it doesn't fit on a page, right? So in this scenario, the page is actually split. So we have to update the parent node to reference 2 new pages. So as opposed to SS tables, B trees are actually mutable. So when we want to update a certain key, we navigate to its page and actually update the location on disk. So this makes writes a little bit slower than our SS tables. But the reason why reads are faster is because B trees are always guaranteed to be balanced. So another reason why writes are slower in B trees is because they are mutable, meaning that there can be write conflicts. So some lightweight locking is needed in order to guarantee that threads don't interfere with each other. All right, so now that we went over the main indexes, let's just do a quick summary of what we learned. Hash indexes, fast, O1 lookup, in memory. Downside, you can't do any range queries. SS tables or LSM trees, fast for writes because they're immutable and do sequential writes. Slow for reads because we need to check multiple different SS tables potentially in order to find our right key. Also, compaction might slow down our read operations. And SS tables have an average of O log n, insert, update, and lookup. Finally, we have B trees, which also have an average lookup time of O log n, but they're better for reads because the tree is always guaranteed to be balanced. There's no duplicate data, so we don't need to worry about compaction. But it's slower for writes because these trees are mutable, meaning we need some lightweight locking to make sure threads don't conflict with each other. And when an update to the B tree needs to be made, we need to load the entire page into memory and update the page and rewrite it to disk. All right, that's all for the lesson today. I hope this was helpful. I honestly learned a lot when I read this. Again, if you like this video and you found it helpful, give it a thumbs up, like and subscribe, and comment, and I'll see you in the next part of the series.